All right, thank you everyone for being here for the latest edition of our One World Minds seminar. Today our speaker is Bohan Chen. Bohan got his PhD at UCLA and is now in the Computing and Mathematical Sciences Division at Caltech. And Bohan will talk to us today about learning enhanced ensemble filters. So Bohan, thank you for being here and please take it away.
Hi, everyone. Today, my presentation is Learning Enhanced Ensemble Filters, and it's my collaborators include Arita, Ricardo, and Edo. They are all at Caltech previously. Now Arita goes to UK and Ricardo goes to Canada as assistant professor, and also with my advisor here, Andrew Stewart. So I will firstly introduce the problem of data assimilation, and then I will introduce a new, we can consider is a neural operator. We call it measure neural mapping. It is a neural operator on probability measures. That is an operator with learnable parameters, but acting on probability measures. And then I will explain how we use this measure neural mapping to learn an enhanced ensemble filter to solve data assimilation for better accuracy and performance. And finally, I will make a conclusion. Firstly, I want to start from the Bayesian inverse problem. So it's like we have such an observation model. Here, X is the data, and H is the observation operator, and eta is the noise. Y is our observation. I put a visual example here as the image in-painting task. If we have multiple images of the indoor scene in the university, so they form an image prior we call PX, and then we have a certain image that is our observation. This observation is partial observation, so we miss some place, and also it's noisy observation. You can see there's some Gaussian noise here. And this is our corresponding observation operator. We assume we know this observation operator H, and we kind of know this noise level, or we can approximate it in practice. And the Bayesian inverse operator is to approximate this posterior distribution from this equation. So here, the posterior distribution is the prior condition on this observation. And if we do a MAP estimation, that is maximum posterior estimation of this observation, then we can recover the true image with a very high accuracy. This is a typical example of the Bayesian inverse problem. And the data assimilation, if I want to use one sentence to describe data assimilation, I think we can treat it as a sequential Bayesian inverse problem. That is, we have a trajectory of some PDE, of some dynamic model, and we solve a Bayesian inverse problem at every discrete time step in this dynamic. Here I have a visualization. This is the Lorenz-96 problem, and it has 3-dimensional. And here, the left panel is the prior distribution, and the right panel is the posterior distribution at each time step. We can see the visualization. This visualization is approximated by a particle filter, which is the high-level idea of it is that we use a very large number of particles to approximate this distribution. But this method is not used in practice because it requires exponential of the dimension of the number of particles. So that is, it can only be applied to some toy examples like this in very low dimensional space. And for this 3-dimensional problem, in order to approximate a very accurate predictive and posterior distribution, I use 1 million particles for this. So you can imagine it's impossible for high dimensional problems. But and also another thing I want you to notice is that here you can see those particles, the blue and the red point clouds, varying a lot within time steps. Sometimes they becomes very strange. That means if we want to solve such a sequential Bayesian inverse problem, we need to deal with varying type of prior and posterior distributions. So it's much more difficult than a single step Bayesian inverse probe. Here is the mathematical definition of the problem setting. We consider state space dynamics and their corresponding observations. Here, we consider discrete time steps. From time j to time j plus 1, we have Vj plus 1. Here, V is the state. And Vj plus 1 equals psi of Vj plus some noise. We call this dynamic noise. And then for each of the state, what we have is their observations. Here, their observations is Yj plus 1 equals the observation operator of Vj plus 1 plus some noise eta. Here we call eta as the observation noise. And with some initial condition. So we usually assume that the initial condition follows some Gaussian, and this initial condition is known. What we know here in this setting is the psi, dynamic, and edge observation, and the noise covariance, and also the initial conditions. So in practice, this psi includes, it is just an integrating of the continuous dynamics over one time step delta t. And what is the problem we want? The problem we want to solve in data simulation here is the filtering problem. There's some other type of problem like smoothing, but here we focus on filtering, and more specifically, we focus on state estimation. The definition of the filtering problem is that we want to estimate the filtering distribution. It is defined as the true state conditioned on all the historical observations, including the current step j. And the state estimation is that we want to estimate the true state from this filtering distribution. There are different ways, but usually people just use the minimum mean square estimation. That is just simply take the mean of this posterior distribution. Any question about this problem setting? Okay. The way from my previous visualization, we can see that this is the data simulation is a sequential process and is much difficult than one step inverse problem. So the idea to solve it is to solve it sequentially. That is, we want to evolve from the filtering distribution at time j, that is pi j, to the next step's filtering distribution, pi j plus 1. And we further split this evolution into 3 sub-steps. That is, we firstly introduce 2 bridges. The first one we call the predictive distribution. That is the state at j plus 1 condition on all the observations up to time j. And then is the joint state observation distribution. That is the joint state, and there is corresponding observation condition on all the previous observations, not this one. To evolve from this pi j to pi j plus 1, we take 3 steps. Firstly, we do the prediction. That is, we evolve from pi j to the predictive distribution, pi j plus 1 hat. And then we evolve from pi j plus 1 hat to the joint state observation distribution. And finally, we do the analysis to evolve from the joint distribution row to pi j to the next steps filtering distribution pi j plus 1. Here, the 3 operators P, Q, and B is defined in this way. Firstly, we have a look at PQ. They are linear operators. Here, this linear is in terms of the operators on probability measures. And we can write them explicitly in this way. And these two are easy to deal with. However, this B, we call the Bayesian inference operator, we can also write an explicit formula of it, but it's nonlinear and is generally intractable. Except in the linear Gaussian case, we can calculate an explicit expression of B, but in nonlinear case, we cannot calculate it directly. So that means if we want to just evolve these probability measures directly from these P, Q, and B operators, it's almost impossible, except the linear Gaussian case. So in practice, people consider the particle method. And to start with the particle method, I want you to have a look at this state space picture, the mean field picture. So the idea is that rather than evolve those probability distributions, we evolve these particles. And the mean field behavior of the particle evolution looks like this. The predict step is just we run the forward model with noise, synthetic noise. And then we extend it to observation. Here, this yj+1 hat is the synthetic observation corresponding to this state vj+1 hat using the observation model. And then for analysis, we want to find an operator. This is mass frac B. And in order to distinguish from this B here, this B is operator acting on probability measures. And this mass frac B is operator acting on vector states. And we want to find such B to be a vector version of the Bayesian inference operator. And we want, and then based on this definition, we have the identity that this B on probability measure rho equals this mass frac B of push for that is the rho j+1 push forward by this mass frac B. Any question here? I'm not sure if this is clear to you. This is just I didn't put the exact definition of the push forward operator here, but it's just like I push forward the density to another space. And based on this mean field state evolution, so people consider the ensemble method. That is because here, if we notice that in the analysis map, although it's in mean field, it still depends on a probability measure rho, and which is intractable in practical problems. So in practice, people use a set of particles we call ensemble to approximate each of the distributions. So for the filtering distribution, we use Vj, and for the predictive distribution, we use V hat, j+1. And for this rho, the corresponding ensemble is the joint of V hat and Y hat. A typical example of this ensemble method is the ensemble Kalman filter. So the idea of this ensemble Kalman filter is that people assume that this analysis map, mass frac B, is affine in the state V and the observation Y. And then write it in this way. And people derive the expression of this K, we call the gain matrix, by matching the first two moments of the linear Gaussian approximation. That is to choose a proper K to match the mean and the covariance in the linear Gaussian approximation. And by solving this, we can get an expression of Kj+1 like this. Here, CVH is the sample cross covariance between V hat and H of V hat, and CHH is the sample covariance of H V hat. Here I want to make a remark. That is, this EnKF is a well-known filter scheme, but this is not the unique filter under the affine analysis of the mass frac B. That is, if we assume that this B is affine, and we want to solve the equation to match the first due moment to the linear Gaussian approximation. There is, in fact, infinite number of choices of such a scheme. And some of them are very interesting schemes, like the square root filter or ensemble and transport Kalman filter. And that means by analyze this affine mean field map and consider the moment matching, we can find maybe some other schemes. Some of them might be better than EnKF. And yeah, people publish papers by analyzing this. And here I want to give a visualization of how EnKF works. So at time j, we have some particles, and we evolve the nonlinear dynamics. So you can see these curves to a predictive distribution. And here, the red star is the observation at time step j+1, so that we use this, we condition this predictive distribution on this observation to get the posterior distribution. And the way we condition it is we evolve it by a affine map. So this is straight line. We go through a sharper analysis map, analysis distribution. Okay, here is a brief review of the problem setting and the classic method EnKF. And the goal for our approach is that we don't want to just assume too much on this mass frag B map. We want to learn it. And there are some previous work. Some people try to learn this mass frag B by a neural network, taking the mean and by replacing this row j+1 by its mean and covariance. So in this setting, you can see, because the mean and the covariance are fixed dimensional vectors and matrix, so that we can design a classic neural network like the multi-layer perceptron for this task. And our design is we don't want to rely on just the mean and the covariance. We want to deal with the measure itself. So that means we want to consider some neural network architecture that allows a probability measure. Here, this is rho, or in practice, is a set of particles as its input. Such a design of a learning scheme is very challenging. There are two major requirements for such a design. We call it measure neural mapping, MNM. The first requirement is that we want it to be permutation invariance. That is, for any bijection, that is permutation sigma. If we permute this ensemble according to this bijection, the output should be the same. We don't want this permute to influence the output. And second is that if we consider some classic filtering schemes, it allows varying ensemble size. We can use a small ensemble size, or you can use a big ensemble size. That means once our neural this BMNM is trained, we want it to deploy it to any finite ensembles, not just a fixed size. So these are two major challenges to design such a map. Maybe I can ask the question, do you have any ideas of what kind of map it should be? Okay, then I will explain our design for such a mapping. We call it measure neural mapping. And so the idea here is we want to use the attention mechanism to design a map on probability measures. So the classic attention mechanism is acting on sequence. And now for large language models, it's still based on the attention mechanism. It deals with a sequence as an input, and it can output the next token prediction. Here, we extend the definition of attention on sequence to attention on probability measures, even like this. This definition is that we consider an attention operator A, which here, this P of RDU is a probability measure on the RDU. And it takes two probability measures as an input. from RDU and RDW, and output a probability the output is also a probability measure. The definition is that A of mu and nu equals a push forward map depends on the second input nu, push forward the first input mu. And the push forward map is defined as this expectation. And this expectation is a tilted exponential distribution. It's an exponential tilted distribution of the second input nu. And this might look a lot to you if you are not familiar, but don't worry, I will explain it in high level later. So I want you to notice that here, although the dimensions are a lot, we can just adjust these dimensions by 3 trainable matrix, Q, K, and V. It's also called the query key and the value in the classic attention. So to let
can I ask real quick? So these dimensions, these are also like tunable parameters. Like you get to choose. Well, okay, so the dimensions of the input measures are probably specified, but the output measure, what is the relationship between the dimensions there?
The output measure depends on the dimension of the matrix V, so it can be tuned. It can be adjusted. And also the dimension K can be adjusted.
Okay. But U and W, those are specified by the data in some way. Yeah, okay.
Yes, they're fixed. So firstly, we want to bridge this attention on probability measures to the classic sequence version of the attention mechanism. That's why we call it attention on measures. So there must be some equivalence. The equivalence lies in the empirical input. That is to say, if we consider 2 empirical measures, mu n and nu m, their lengths can be different. And then we have that the output of attention of these 2 empirical measures is also an empirical measure with n samples. That is, it has the same number of samples of the first input. And it can be expressed in this way. On the other hand, if we don't consider these 2 as empirical measures, we just stack this uj into a matrix capital U, and we stack this wk, that is the samples corresponding to nu m, into a matrix W. The classic attention is defined in this way. And we have equivalence that this is the sample of the J sample of the output empirical measure is exactly the rho J of the classic attention defined by these 2 matrices, if given that this Q, K, and V are the same. The key thing here is that the softmax can be treated as an exponential average, so that this exponential average is explicitly written in here. So from this theorem 1, we can bridge the classic definition of the attention mechanism to this measure-based attention mechanism, so that we can study on this measure version of the attention. The second theorem is I just proved it last month, and I'm still writing the paper. I will put it on archive soon. It is, we call it as the continuum limit of the attention mechanism. So here, we only deal with the attention on probability measures. Under some decay conditions, to be specific, we need it to be equal or faster than Gaussian decay. Then we consider these 2 probability measures, mu and nu. And if we consider some IID samples of these 2 distributions, we have their corresponding empirical measure, mu n and nu m. And we consider the y-system p distance for p greater than 1. We have 3 versions of continuum limit. The first one is on the cross attention of the first input. That is here, all the expectation is with respect to these discrete samples. The expectation of the y-system distance between this A of first input as the empirical measure, and this first input is the continuous measure. This will be 0, the limit of this expected y-system P distance. And the second is about the second input of the cross attention. And the third is about the self-attention. So the last one is the most difficult because there are two, and the first and second input are changing in this way, and that they are correlated to each other. So this theorem is very important. That is to say, if we want to use this transformer attention on probability measures to approximate something, we can just, in practice, we can just consider a finite set of samples. And if we have enough samples, the difference between this discrete version and the continuous version will not be that different. And in fact, I can provide more detailed decaying rate for this. So it's like, it's not decaying very fast. It's nearly like n to the -1 over d. Here, d is the dimension. It's similar to the decaying rate of the y-system distance itself. Any questions about this theorem? Okay. Okay, based on these two theorems, and now we can just safely use the attention mechanism as operators on probability measures. And then I will introduce how we design a transformer-based measure neural mapping. Here, let C and S to be self and cross attention blocks. I say blocks here means that it's not only a simple self or cross attention layer, it is the layer itself with residual connection, with layer normalization, with feed-forward layers. But this won't influence the overall theorem or the properties, because all these operations and the layers can be treated as element-wise push-forward map on those distributions. And then the goal to use this transformer measure neural mapping is that we want to encode, because previously, as I said, the most difficult part to learn such a map is we want to deal with input and probability measure as an input. So that we want to encode this probability measure rho into a fixed dimensional feature vector to represent it. To deal with this task, we introduced the transformer-based measure neural mapping. We called it FTMMM. The design of it maps a probability measure into a fixed dimensional feature vector in DS. This is also adjustable. The design of it is that, firstly, for the input measure, we have Fin is a feed-forward neural network of it, like a standard fully connected layer. And then the encoder is a composition of several self-attention blocks. And the bottleneck is that we have a trainable empirical measure. I will explain it in detail later. That is do the cross attention with this trainable empirical measures. And then we do a decoder of the attention mechanism, and we have some final feed-forward layer. So such a design is motivated from the set transformer architecture. The set transformer is designed for this task. It wants to map a finite sequence into a fixed dimensional feature vector, and its design is almost the same as the transformer measure neural mapping. The tricky part in the set transformer is that in the bottleneck layer, it has a trainable sequence. We call it seed. It is a trainable sequence with a fixed length and a dimension. That is when then we do the cross attention between this sequence and the second input. An advantage of such a bottleneck layer is that, do you remember previously I mentioned that after the after the attention mechanism, the output has the same number, the output has the same length as the first input. So that after this bottleneck, no matter how long the second input is, the output of this bottleneck is always has the same length of the first input S, which is fixed and given. And then also the dimension is also the same as the dimension is also fixed. So that after this bottleneck, no matter how long your input sequence is, after this bottleneck, it becomes a fixed length and a fixed dimensional sequence. That's the tricky part of this seed. And it's shown in the original set transformer paper that the set transformer architecture has two major properties. The first property is the permutation invariance. That is, for any permutation, the output is the same, no matter how you permute the input sequence. And the second is the variable input length. And this is because of the bottleneck cross-attention part. That is, no matter once it is trained, you can use different input lengths and the output is always the same. From this first proposition, we can just treat a sequence as a set or empirical measure. From this proposition 2, we can bridge because we can use any finite length of the sequence. So we can use this proposition 2 to bridge the empirical measure to a continuous measure. And these two propositions are shown in the original paper. And these two things are the additional ones of ours. The first one is that we say in the transformer measure neural mapping design, here the input is the empirical measure. It equals to the set transformer with a sequence of these samples. These two are the same. And the second is the continuum limit. That is also our major theoretical contribution of this transformer measure neural mapping architecture. That is for any IID samples with mu with some tail decay conditions. We have that this transformer measure neural mapping of mu n as input converge in probability to the transformer measure neural mapping with the continuous measure as the input. And here I want to emphasize that this convergence is in the space RDS. So it's not in the probability space, it's in the vector space. And this theory is very important and very difficult. That is because although I assume IID for the initial input, but the transformer itself is a composition of several attention blocks. And we can imagine after one attention layer, it is no more IID. Because the self-attention is just let each sample interact with all the other samples. So after one layer, it is no more IID, but this property still holds. So that means we can, so in summary, we introduce this TMMM, which acts is a Liouville operator acting on probability measures. And it's equivalent to the set transformer with empirical inputs. And in Ensemble, so that in the Ensemble filtering setting, we can use a set transformer to deal with the sequence input or the Ensemble input. And because of our theorem, that means we can link the Ensemble methods to its mean field limits by the convergence theorem of transformer measure neural mapping. And we have some guarantee that the output stays close when we change the ensemble sizes. So that means that has some practical advantage. That means we can train at one ensemble size and deploy at different other ensemble sizes. So up to here, we have addressed the two major challenges I stated before. That is the permutation invariance and the varying ensemble sizes. And also we have abundant theoretical guarantee to using this setting. Okay, and next I want to introduce how we use this machine learning mapping to learn the ensemble filter. The idea is that we want to keep the predict and the extend, these two steps, as the same to all those classic filters, and we want to train this analysis map with triable parameters theta, and here the input is a finite set of ensembles. The idea is that using the set transformer, we can encode this state observation ensemble to a fixed dimensional feature vector. And then we can use a multi-layer perceptron to deal with, once this becomes a fixed dimensional feature vector, we can use a multi-layer perceptron to deal with all these inputs. And further, we further assume that this B theta has a similar scheme to the ensemble Kalman filter. And what we learn is the correction terms in the gain matrix, as well as the inflation and the localization. I will further explain the advantage of such an inductive bias of EnKF. So here are the detailed design of our MNM-enhanced ensemble filter. Firstly is that we encode this empirical measure by the set transformer. It looks like this. Here, the empirical measure or the set of ensemble becomes a fixed dimensional feature vector. We call it FV. And then this is the core of our approach. We want to learn a corrected gain matrix in addition to the ensemble Kalman filter. The design is here. If we remember the previous duration of the ensemble Kalman filter, that is K equals the covariance times an inverse of another covariance. Here we rewrite this two covariance matrix as K theta 1 and K theta 2. These two matrices are the original covariance matrix, this part corresponding to the original covariance matrix, with a learnable additional term. This W theta is corresponding to the state, and this Z theta is corresponding to the observations. And the gain, the way we learn it is that we want to train a MLP that is taking the state is observation and the true observation, and also the feature vector from set transformer to get these two correction terms, and put these correction terms in the calculation of K theta 1 and K theta 2 to calculate this K theta. And in addition to this learnable gain matrix, we recall that in the classic method, people usually use inflation and the localization tricks to deal with insufficient ensemble size. That is, for a very small ensemble size, people will consider this inflation and the localization. So similarly, we also introduce trainable inflation and the localization. The classic inflation works in this way. That is, it adjusts the analysis and the state after the analysis step. It adjusts it by some constant alpha greater than 1. The idea is that it wants to push each particle away from its mean. And here we replace this push away term by a learnable term, U theta. And this U theta depends on is an output of such an MLP. This MLP only takes the state Vn and also the set transformer output here. This is learnable inflation, and the adjustment becomes, after the analysis step, we adjust it by this learnable inflation. And also we have learnable localization. The localization idea is that people want to adjust the covariance matrix by some distance to weight functions. The idea behind it is that if the ensemble size is not large enough, there might be some fake correlation between certain dimensions, so that we will eliminate some the correlation if the distance between two dimensions are very large. These dimensions can correspond to the spatial discretization of the PDE. For example, if we do a Navier-Stokes equation and the two grid points are very far away, so we don't want they have some very strong correlation. So we will reduce the correlation between them. And in the classic setting of this localization, people just use some given distance to noise function, we call it G here, to map the distance to, not to noise, sorry, distance to weight function G here, to map the spatial distance to some decaying weights between 0 and 1 to reduce the correlation between faraway points. And here we introduce a learnable distance to weight function G theta here. And this this function only depends on the output of the set transformer FV. I skip some details here, but the basic idea is that we want to use some inductive bias from the classic filtering scheme. Many people may ask, why do you just simply learn end-to-end map B here? Because we have the expression of B, and why do you just learn it directly? So the way we learn it is that we assume inductive bias to learn it, and it has at least 3 major advantages. The first one is interpretability, because as I said before, each component of our learning scheme has a clear function. The correction terms will deal with the nonlinear and the non-Gaussian setting based on the EnKF, because we know EnKF is optimal for linear Gaussian setting. And also we have the inflation and the localization part, components which function similarly to the inflation and the localization in the classic method. And also we have the set transformer, which only function as an encoder to encode the empirical measure into a fixed dimensional feature vector. So each part is interpretable and we can adjust them easily. The second is numerical stability. By considering such correction terms within K2, we don't directly modify K2, but we consider correction terms within it. That is to guarantee that K2 is, the learned K2 is still positive semi-definite matrix, so that this inverse matrix, this matrix is always invertible. And the third part, a third advantage is that it makes the training easier. This is related to the data simulation problem itself. It's not just a one-step inverse problem setting, so that the training loss should depend on, I will introduce the training loss later, but the training loss should depend on the entire trajectory. That means if we don't start from a good initialization, the training loss will be very huge because all the dynamic system are Caltech, so the filter might diverge to some other places. So that we want to make it easier for training, so that we want to start from something we know that is reliable. Okay, here for the training data. As I said before, we assume we know the dynamics, observations, and the covariance. So we use synthetic training data. That is, we firstly random sample initial state from the invariant measure of the dynamic system, and we do the simulation according to the dynamics and observations. And for example, for Lorenz-96 dynamics, we generate 8,000 trajectories with the length 60 for training. And the loss is the normalized mean square error between the estimated states and the ground truth states. The way we calculate loss is that firstly, we have an initial ensemble based on the initial distribution. We assume we know that. We sample initial ensemble, and then we run the forward model to get a predicted ensemble and run an analysis map to get an analysis ensemble. Here, the analysis map is parameterized. And we have a state estimation using the mean of this ensemble at each time step. And our loss is calculated based on the mean and the true state with some normalization. And the loss is So it's firstly average across all the time steps within the same trajectory, and then average across all the trajectories. There are two remarks. Firstly, our model can be trained from one ensemble size to another because of the set transformer. So for efficiency, we can start trained from a very small ensemble size, for example, 10, and deploy to larger ensemble size for better inference accuracy. And also, lightweight fine-tuning is applied to further improve the performance. I say it is lightweight because we freeze the set transformer part, which counts about 80% of the accuracy. This is because the theorem of set transformer we have, once we have a set of trained parameters and we adjust their sample size, it won't differ too much. And what we fine-tune is the MLP parameters related to gain, inflation, and localization. This also comes from some inductive bias from the practical method, because in practice, when the ensemble size changes, the inflation and the localization parameters should be changed. Here are our experimental results. Firstly, is the Lorenz-96 problem, and its original, we use a 40-dimensional Lorenz-96, and our observation is 25%. The dimension is 10. And this is the result. We compare to 3 benchmark methods, that is EnKF. IEnKF is iterative EnKF, and LETKF is localized ensemble transport Kalman filter, which is also a leading method. I want to further emphasize that this benchmark method also have some tunable hyperparameters, that is for inflation and localization. We did a very wide range grid search to guarantee that all these hyperparameters are nearly optimal. And this is the improvement, relative improvement in the relative RMSE. So we can see on Lorenz-96, the improvement is nearly around 10% when the ensemble size is large, but when the ensemble size is small, the improvement are very significant. And another test is Kuramoto-Sivashinsky. It's an even more difficult scheme. It's a PDE scheme. And here we consider 128 dimensions, and the observation is even more sparse. The observation dimension is 16 every 8 dimensions. And we use a ETDRK4 scheme for the numerical integration. So the result on this one is better than the Lorenz-96. That shows our method has more advantage for more difficult problem, and the relative improvement is around 20%. As a conclusion, today I introduced the MNMEF, that is a novel machine learning-based state estimation method for the data simulation, and also a measure neural mapping. We extend the transformer to as a map on probability measures. There are lots of filter work based on this architecture that includes different loss design. The current loss only focus on the state estimation, but we can definitely consider some probabilistic loss to really learn the true filtering distribution. And we can also consider some general filter that is end-to-end. And also we can consider amortized operators based on different dynamics or observations. And the last part is the theory part. We still need to prove something related to universal approximation for this measure neural mapping. Thank you for your attention. And you can scan this QR code for our paper on archive.